So the next session is on energy efficient supercomputers and data centers, and it's appropriate we have Fred Chong, who's chair of the computer engineering department at UCSB, to moderate this section. So Fred?
Hi, welcome back from the break. So I'm very pleased today to have three great speakers to talk about some of the challenges of computing at very large scale in the sort of supercomputing and data center space. I think that if you're following the media, I think that the energy footprint of data centers has been getting, for better or for worse, lots of attention. I think there was a New York Times article recently that mentioned that the electrical footprint of data centers is fifth if you counted it as the footprint of a country. So it's a little bit sensationalist, but I think it brings a lot of attention to the problem. I think that one of the interesting things is what are the benefits that these data centers bring, as well as how can we make them more efficient. So we have three great speakers today. We have Horst Simon from Lawrence Berkeley Labs. We have Pradeep Dubey from Intel. And we have Bikash Koley from Google. And they're going to give us different perspectives on these problems and challenges and opportunities that we have. So first, we'll have Horst Simon, who's going to talk about sort of the science that's supported by large-scale computing. Horst is the Deputy Director of Lawrence Berkeley National Laboratory, and he was also, I think, the first director of NERSC, which was the National Energy Research Supercomputing Center, right? And he brought, I think he also started the sort of computational science arm of Lawrence Berkeley. So he's really well positioned to talk about how supercomputing enables science, and also what the challenges are of computing at that scale.
Thank you, Fred. It's a great pleasure to be here, and I would say my talk is somewhat different from the other talks because many of you have proposed solutions, and I'm going to just talk about problems. So it's actually always easier to just talk about problems. But what I would like to talk is first a little bit about exascale computing. What is exascale? 10 to the 18 operations per second. It's a big number. It's a number out there that we've put ourselves because it's something to measure progress to, but the issue really is to look at the next generation of supercomputers and high-performance computers and see how we can enable science. And I'm drawing, in the first part of my talk, a lot on a group of colleagues who have worked on this for many, many years. And what we've done is, since about 2007, developed the case for extreme-scale computing, for exascale computing, worked in many workshops, delivered many reports which look at all these activities, and they're all available on the web so you can look at them. And it's very difficult, of course, to look at 10 science reports and 2 computer science architecture reports and extract from them in a few slides what's going on. But let me just sort of at the very high level say why we continue to push at the supercomputing field. And I think that's very important to keep this in mind because a lot of you may think and say, well, supercomputing, this is something that has been solved or was done in the 90s. But if we look at some of the big challenges, societal challenges such as climate change, all the things that we've discussed today in terms of energy, reducing reliance on foreign oil, and if we look at national security posture that is still continue maintaining a stockpile of nuclear weapons and a deterrence, and understand how that stockpile ages. If we look at all these missions, then you see that in all these cases, supercomputers play a significant role in modeling and simulation and continue to play a very important role in developing the modeling and simulation capabilities to continue a leadership role for us in the US. So here are a couple of the science challenges, and I could go into all of this in great detail, and I fortunately picked a few that we're doing in Berkeley, and I actually have only time to talk about one. And the one that I would like to talk about is first principles calculations for materials, the Materials Genome Project. That's a joint project with MIT. And I've picked this one really with a look at the program that what you're talking about, and I think Bill Brinkman mentioned this, that we're at an age where with exascale computing going into the future, we can design more and more things just using computational power. And so in electronic structure calculations, we have demonstrated in many instances the predictive power of computational simulations, and we can predict through computation a number of properties of materials that are listed here. And the idea is then, so take all this information that's merely based on computation, on validated computation, put it all in what we want to call the materials genome project, or what you might call the Google of material science, where all these calculations, all the results are available. And if you have an idea about a certain material, that you could actually look it up and see what has been calculated, that this is in a scalable infrastructure, a large database. And so what it is, I think, a perfect combination of the challenges that we actually see in the next couple of years in computing, that on one end, in order to do all these simulations, you need very high computational power in the petaflops to exaflop range. On the other hand, it becomes an automated data structure and infrastructure that we need to build to support all the data that come out of a calculation. So, for example, this approach that was actually pioneered by Gerd Cedar at MIT has already led to some very promising discovery of new materials that could be used for battery technology. And the interesting thing is that if you look about this, you can apply this technology, this computational technology, for anything where you need critical materials. I mean, we haven't talked about it, but I don't see any difficulty in looking at this, say, for example, for photovoltaics or for looking at other critical materials. So this was just a very simple example of how computation is continuing to use very powerful supercomputers, and as we move in the future, that we continue to need these very powerful supercomputers. So the next two pieces of my talk, I want to talk about the last decade and the next decade. 1999 to 2009, the last 10 years, so to speak, was the jump from teraflops to petaflops. 2009 was the year when petaflops became available. So let me first take a very simple summary of where we are today, because you may have heard that the Chinese have now the #1 supercomputer. This is a great accomplishment, but if you look at the substance of using computational technology and using, in particular, computational modeling in engineering and science applications, the US is by far still the leader. Here's the top 500 list from November 2010. This is an activity I'm involved and have been involved with since 1993. That lists the 500 most powerful supercomputers. If you look at the list, you see all the labs that are actually 3 labs under Bill Brinkman's direction, the other 3 in the NNSA. So 6 of the top 15 systems are actually in the Department of Energy. And here's actually, I don't have a slide about Berkeley, but at least at this point here, I want to make some Berkeley commercial. This is the latest system here, number 5, just about a petaflop, the Hopper system that was just installed a couple of months ago in Berkeley. So we are in a very thriving, very successful environment using high-performance computing today. And this is based on probably 20 or more years investment, not just in the computers, but into computational science, computer science, and applied mathematics, which brought all this together to make it possible to use high-performance computing for scientific applications. So I'll show this very quickly. For the specialists, there are some characteristics. The most powerful system in the US is the Jaguar system at Oak Ridge. Here are some characteristics. 10 years ago, the most powerful system in the world was this system, the ASCII red system that was at Sandia National Labs. And here are some characteristics. The important thing is on this slide. This is about the ASCII red system was the first teraflop system. And I use the Jaguar system because it's very easily comparable. If you look at sort of this decadal comparison, how we got from teraflops to petaflops, you will notice the following is we got about 1,000 times more performance on this benchmark called LinPack, but we only have 24 times more processors. So yes, we did use parallelism, but we almost made an equal contribution by, in a sense, taking advantage of Moore's law and the increase in processor performance of individual processes. That's what's basically a free ride, because in a sense, high-performance computing, supercomputing was living on the industry growth and on Moore's law and on providing more and more powerful microprocessors. So that's one important thing to look back. The other one, when you look back by a decade, is that it was a significant increase in cost. The power of the Jaguar system is almost an order of magnitude, almost 10 times bigger than the power requirements for the ASCII red system. And this is really the trend that we need to be very aware of, because this, unfortunately, if nothing gets changed, will continue like this in the future. The other important thing is these two systems are essentially the same architecture, the same environment. You could take a program that was running on ASCII Red and it would run on Jaguar, more or less, without much thinking. So something important happened in 2004. And in all important things, there's sometimes a time when you look back that you know something important happened. And I think I actually can pinpoint the change in 2004 to the specific event, which was when Paul Ottolini from Intel declared that Intel is no longer sort of building faster microprocessors, but they will go to multi-core chips. The reason that was driven was because if you look now at the technology curves in the early 2000s, you see that we reached sort of the flattening out at about 100 watt in terms of the power per chip, and you see that we see that the speed of the chips are flattening out about 3 to 4 gigahertz. And we have not seen increases in power consumption because that's sort of the limit that you can put on a chip, and we consequently also have not seen increases in the clocking of those chips. So from now on in the future, Intel declared, so in 2004, everything will be parallel, will be multi-core. So what we have is that because of the power constraints, the industry response was simply to double the number of cores per chip instead of doing the clock scaling. And therefore, we entered actually the time of truly massively parallel computing in 2004. So many of you may be around, and I've been also a veteran of the early days of massive parallel computing in the early 90s, and companies such as Thinking Machines and that were around then, and everybody says, oh, this massive parallel computing didn't work. Well, it was just 15 years too early. Like somebody else said, the future is here already. Intel came, and IBM came, and they all built a multi-core system now. So parallelism is here, and parallelism is here to stay with us. So I mentioned the top 500 already. That's an interesting exercise in listing the top 500 supercomputers. If I had more time, I could tell you dozens of interesting anecdotes on how systems and countries wrangle to be number one and make the list. The remarkable thing about this top 500 is you take a supercomputer, you run this benchmark. The benchmark measures a floating point operations per second number. It's called the Rmax number, and that determines your position on the list. Individually, it's not that interesting, but in aggregate, it gives you extremely reliable statistics on where the industry is going, how things have grown. And so what you see is if you sum up the 500 systems on this top 500 list, you get this remarkable linear growth. And this is on a semi-log scale, so exponential growth. And it's pretty amazing that in a process that is really driven by what vendors do and what customers do, that we get this logarithm of this exponential growth. For number one system, it's a little bit bumpy. You see these big bumps up. This here was the famous Japanese Earth simulator. It was a big jump up. Then you see here jump up, that was Blue Gene. Then this was the Roadrunner. So you always get some big system that bump up the curves, but on average for some or also for number 500 stay the same. And you see how remarkable the growth was that here the number 500 system with 31 teraflops would have been faster than the Earth simulator, the most talked about system in the early decades. So Moore's law, more parallelism have pushed this curve forward. Now the reason I show you this curve is just because what a lot of my colleagues and I did and myself are doing is this following. You just extrapolate this curve into the future. And then somebody says, so by definition, we get the exaflop in 2020. Case done. Just wait and sit and relax. Well, I'm trying to set this up. No, this is not what's going to happen because, I mean, you should all be very careful. Even if it's late in the afternoon, you don't extrapolate an exponential curve. You shouldn't extrapolate at all, and in particular, an exponential curve, even a small variation can introduce big errors. So this is really the problem with relying on the top 500, that you think this is happening automatically. It was actually remarkable how automatically it happened in the past decade or in the past 20 years. And this is truly because we entered a technology, the CMOS microprocessor-based supercomputers, in the early 90s, and we stayed on that technology curve until now. The systems that were built in the early 90s are essentially the same systems that we have now, just writing Moore's law and making slightly more parallel. Anyway, what is going to happen is concurrency, and I alluded to this already. The new Moore's law really means performance doubling can only be achieved by increasing more and more parallelism. And if you look at the maximum on the top 500 list, which is now in some big systems, like, for example, the Roadrunner or the Jaguar system, or also the Hopper system, these are about 100,000 to 200,000 cores. So if you extrapolate this, you see the big system will hit the million core and then the 10 million core very soon. And the interesting thing is that if you sort of plot your laptop, and this is what you have to think about, you may have had a dual core in 2006, 2007, and if you have a state-of-the-art laptop with some NVIDIA accelerator, you may be in 11 by already having 100 cores. But this is sort of the other thing. You really have to deal with also parallelism on the laptop, desktop level. And of course, companies like Intel and Microsoft have already many years ago started investing in this and thought about how parallelism will be used in the laptop. But for the supercomputing, clearly parallelism will go up. This is one big challenge which make the exaflop system much, much more different from what we have today. So just in short, what I have talked so far about is number of cores will double every 2 years. Clock speed will not increase, maybe even go down. We need to deal with huge systems with millions of concurrent threads, and we have to deal with parallelism on the chip and between chips. So let's come to the power consumption, energy on these big systems. So if you look at the top 500 systems and see what's their power level in terms of kilowatt, you see that the top systems are in 5, 6, 7 megawatts. That's a huge number. If you don't think about it just for a moment, just simply multiply this by a million. It's just, depending of course what your local utility costs are, a 6 or 7 megawatt system will cost you, roughly speaking, $6 or $7 million a year in electricity bill, more or less. So this is a huge issue, and in particular it's a huge issue because 5, 6 years ago all the systems were down here in the below 500 kilowatt, and it was not an issue because that was adding on top of a multi-million-dollar system just a small operating cost. Now, this is one trend. The other trend is that the energy efficiency actually in terms of, the power efficiency in megaflops per watt on these systems has actually been improving. In particular, multi-core and many-core systems automatically improve the efficiency. So we have really two trends. The systems get bigger, but there's also more power efficiency per calculation. So there's a very, very interesting paper that unfortunately hasn't gotten as much attention as it should have gotten by Jonathan Koomey, who did a very thorough analysis, and I call it Koomey's law. He doesn't call it this way. Gordon Moore took 3 data points and created Moore's law. Jonathan Koomey went back into the 1940s, 1950s, looked at all the old papers. He went to the Computer History Museum, did benchmarks on historical machines, and derived that computations per kilowatt hour have improved by a factor of 1.5 per year over a long historical period. So that's a terrific data point to have. That's in IEEE Spectrum last March, because now we have sort of what the industry has been doing. So the fact that many cores are getting more energy efficient is really not anything different from what happened in the past. Computers have become more energy efficient. So here we are today, and the key question is we have these two trends. We have computers become bigger, become more parallel. Individual components, by industry standards, become more energy efficient. How do these two trends really, so to speak, multiply together? Well, it's a very simple analysis. Koomey says we have 1.5 improvement in computations per kilowatt hour. For supercomputing data, top 500 show that's about a 1.86 increase on computations per second per system. So overall, basically the power per system has been increasing at about 1.24 per year. And if you take this together, you can project that a exaflop system, which will run half an exaflop on Linpack, say in 2020, will require 60 megawatts. 60 megawatts means $60 million to pay electricity. So of course, hopefully we'll get all these photovoltaic plants built and have a gigawatt plant right next to the supercomputer, because otherwise we can't afford this. Well, this is a real back of the envelope calculation. You may doubt this, but Peter Koley did with a group of scientists and some of my colleagues a very detailed study on behalf of DARPA in 2008, 2009, and pretty much came up with the same results. So here is the sort of linear extrapolation that would come out for top 500. Here are the top 10 systems from the top 500. And here is the expectation that how you could get to the exaflop. The interesting thing is the DARPA study said you can't get to the exaflop just based on the technology curves that were at that time projected by the vendors, just using standard technology. But the real interesting output from the DARPA study was that they came up with a number which was of about 120 megawatts per system, per exaflop system. And this is twice what I said, but it's an exaflop system. So it's about in the same ballpark. So I pause at this point. I live in a lab which was 30, 40 years ago, a high-energy physics lab. And we know what happened to high-energy physicists. They built bigger and bigger systems until they built the last one. And I don't want to retire as computer scientist proposing bigger and bigger systems until we build the 500 megawatt supercomputer, and then I won't build another one. So something needs to be done about these systems. Well, this group that I mentioned before went and looked at exascale systems and said, we really have to limit in 2018 the exaflop system by about 20 megawatts. That was really a decision, a design decision. This is a goal that we can live with. And then we have to look at all the other technology. So if you want to do this, these are sort of the constraints. All performance is more parallelism. So we have to really deal with a lot of parallelism. That's good news for all computer scientists. Many projects to do. Good news for mathematicians. Here is the good news for the technologist. We want to increase the power only by a factor of 3. So we have to invest a lot in computer architecture, new technology research. And it will be a significantly different software systems architecture. And of course, we will have to run different applications. So here are 2 references on where you can find all the details on it. So there's another 40-minute talk, and I'm out of my 20 minutes now, which will talk about all these things and what can be done in these areas. So John Bowers did a terrific job talking about data movement, for example, and silicon photonics. Certainly is a technology that we will need to reduce the energy, the power consumption in the supercomputers. But there are many other things. Processors and memory have to be closer together. There's a question of stacked memory. In terms of memory technology, we have to look at resilience technology. So this is, as I said, another hour and a half talk with about 20 minutes or 50 minutes on each of those topics. The main message that I want to bring to you here today is that unlike many of the other exciting technologies that we've heard today, with maybe the exception of the silicon photonics and some memory technology, industry has not yet picked up on this because they think of supercomputing as something that's esoteric, not interesting, old application. What's missed here is that this is the future of computing in general. Energy efficient computing will drive the future of computing, just like energy efficiency is driving everything what we're doing here in terms of lighting or photovoltaics or batteries. Consequently, there is really an opening to develop new technology that will lead to probably dramatic breakthroughs and change computing in the next decade. And whoever is going to be first in finding some of those gaps will be successful. So here's my summary. I think I said what I said in a summary in the last slide. Computing will significantly change. Power and parallelism will drive changes in the high-end power consumption, energy efficiency at the low end. And we really need these new technologies to get to the exascale level. And those technologies are really in the infancy today. Thank you.
So we'll take time to ask a couple questions after each speaker. And then since time is pretty tight this session, I guess we'll defer more questions to the reception. So take a couple questions now. Let me ask one while we get the mic going. So you talked a lot about sort of total power consumption of these systems, but I think that there are also some power density issues in terms of,
So I didn't talk about the whole other issue, and this is, if you look at systems require more and more power, then at one point you reach your limits in terms of the facility. Your computer room is too small, you can't provide the power to the room. And so this is the other trend that we're seeing in terms of where cloud computing comes in, of course, high energy efficient data centers. And I think the next speakers will probably talk about this.
I'm curious how far you think you need to go on optics, chip to chip, intra chip, or board to board. Where do you think you need optics?
So that's a difficult question. I think if you just look from where a lot of the energy we need energy is for actually data movement. And so this is data movement from chip to memory, from processor to memory, and then also, of course, node to node. So I think that the optics in terms of node-to-node communication is probably easier to do than the integrated optics and even on-chip optics. But if that can be done in the time frame, we should do it. So I think if you look in terms of priority, it's really the memory bandwidth question and doing this in the most energy efficient way.
So I suppose the supercomputer results will tell us that they are becoming more a significant cause of global warming as they become more powerful. Is that correct?
Yes.
No, but
that has been an issue.
But I guess related to that in terms of efficiency as the topic of our seminar, is the use of that, flops per unit of power, is that something that could be used not to make the computer much more powerful for the home user who's sitting there with a computer waiting for him all the time anyway, and instead make that a more efficient computer that will take care of your basic home computing needs without using so much energy?
So I think there are a couple of different issues. I would say computing in general, let me make a very direct statement. Computing in general has been so far pretty much up to date only about performance. If you, and this is also true for consumer electronics, if you buy an HD TV at home, you're not looking at the power consumption. You want to have the biggest screen. If you buy an Xbox or something at home, you want to have the newest, fastest, high-performance thing. You're not going to look at whether this is a 200 or 400 or 600 watt consumption. The same is true at high-performance computing. It's all still about performance. So I think there still has to be a mindset change in terms of what we look at across the whole electronics industry. Energy efficiency is not a topic. So that leads to a question of what are the right metrics. And I think, again, this is also not yet really well defined. There are metrics that measure the efficiency of data centers, and there are metrics that measure the efficiency per calculation, but it's not really clear what we should really strive for. So I think all open research questions.
I guess the equivalent would be we don't all buy hot rods for
Yep. In computing, I mean, why do people buy an iPad too? Because it's the next new thing. You always buy the next thing. It's still a mindset that we're really deeply in it, and it's from your cell phone up to the supercomputer. It's always the same mindset.
Thank you very much for that really fascinating discussion. And I agree with you about a certain limit, a certain threshold of Moore's law, if you will, that will eventually be hit. But at what point does co-location of these kinds of facilities adjacent to power production facilities buy you a certain amount of time to figure out how to address that evolution?
Yes, they do buy some time for, in a sense, the type of calculations that are amenable to co-location, that is very data-intensive applications, in a sense what the buzzword cloud is referring to. And I think the first barrier that a lot of data center managers will hit is the question that the point that they can't put any more servers in the data center, that they have to build a new data center or that they have to get additional power. And at this point, the incremental investment is so high that you want to go into a co-location center. That's sort of, but as you said correctly, the processor technology, the memory technology, whatever the large co-location centers are using, is not different from what you use in your home. It's still what the industry is driving. So what I'm talking about is that there are a couple of technologies that really need to be introduced across the industry from, in a sense, from the cell phone to the supercomputers that make it more energy efficient. And we have to think in the industry more about energy efficiency.
Great, thank you very much.
Thanks.
So our next speaker is director of the Parallel Computing Laboratory at Intel. I think that's very appropriate for the massive parallelism that we're discussing today. And I think he offers a fairly unique perspective in that his group looks at a very vertically integrated view of how to optimize applications for specific architectures to be more efficient. Pradeep, before becoming director of the Parallel Computing Lab, also designed many of the vector extensions for AltaVec and MMX for that family of microprocessors. And I think that, once again, I think that this perspective on applications is going to be very interesting for us.
Thank you. Good afternoon. My boss was supposed to do this talk, Justin Ratner, and he would have definitely done a very different talk. And I first thought about just doing a pitch that he would have done, but that would have been just artificial. And you would certainly not see an Intel presentation without Moore's law, without billions, millions, powers, transistors. And I thought about it and I decided to take a gamble. So this is a different talk, a talk that I can do more naturally based on my IBM research experience and here at Intel. And this is not a single graph or plot or number or millions, picojoules, anything. So it's definitely yet another attempt at different talk. So first of all, who we are Parallel Computing Lab. And to complement what rest of the Intel, or rather rest of the industry does, we don't go bottom up, we come top down, right? And of course, it's a matter of iterating. So we do vertical stuff, which we hope rest of the industry doesn't do. So when we're working with a company, whoever, right, Google's, Apple's, or Wall Street's of the world, our mindset is very different. It's as if we're building a system just for that one guy or that one application. It's that mindset is how we do this research. And in the process, we discover or we figure out what's the most optimal system design point is. And if that's too far off from what we are building, something will happen. And therefore, we'll have to address it. And that's exactly what has happened. The big outcome of this research is a new processor roadmap that you probably have heard of, something called Mike, which directly came out of this research. So I'll refer to that in the second half of my talk. So like I said, we start from the top. We work with just handful academics and industry players. We only pick an area if we find an industry co-traveler as well as an academic co-traveler. It's between the two of them that somehow the equation, somehow everything completes. And we are incomplete if we only found one of them. So and then we get going, and the primary focus area at this point, I just briefly listed where we have been focusing on architecturally and workload-wise. And then try to go into more details. Architecturally, our biggest problem that we are facing at this point, we are past that point in our first generation of this research. In my previous first 4 or 5 years of this research at Intel, we are mostly talking about needing more cores. And I joined Intel 2003, and we are still talking about single core machines, Itanium ruling the world, and such things. There was no multi-core mindset. Right, and somewhere there, as I think 2004 or Ottolini talk or whenever this happened, and now we're at a point where we already passed the point of number of cores or flops. Only enough, too many flops rather. The real challenge has shifted from compute to data. So the primary architectural focus is feeding the beast, right? How do you really feed data to where the compute is? And compute is least of the problems in many ways. And the other challenge is that it's very difficult to come up with solutions that work in general. So we are really focused on domain-specific solution, graphics being a good example of how problems have been tackled and become simpler when you focus on a domain. I mean, I did a lot of my time at IBM was spent during speech recognition. Same thing, a problem in general may be hard. You focus on a domain, and now good enough speech recognition systems are sold to radiologists or in cars. So the focus and narrow the domain, and you can offer and you can see significant acceleration opportunities. Finally, we are looking at not the 2-4 thread machines or 100 core machines. Those are there. But the way you go from 1 core to 2 core or 1 thread to 2 thread or 10 thread is very different than how you go from 10 to 100,000. So we are looking at how do we build massively multi-thread machines. And the last two are also very important topics. So somehow, anyway, unstructured accesses. Most of our focus is on unstructured accesses because most of the problems now are irregular data problems. So the regular problems are relatively easy, and most of the world out there is not relational databases but unstructured blocks. So our primary focus architecturally and research-wise is really on understanding irregular large data sets, irregular problems, unstructured accesses. In one word, the workload is simply massive, large data set, multidimensional data set, and you have to index it, right? So finally, the interesting part of the talk, interesting part of our research is distributed decomposition, because distributed decomposition hasn't so far has always been around, but it's becoming a much more of a requirement, and I'll offer some of the motivations. So most of the time we no more are struggling trying to break the problem into few cores and integrated CPU, GPU on die. We're doing that. But the real challenge, the real ROI, the real return on investment happens when we can actually decompose the problem over the cloud, and that's where the real efficiency and return happens, when you can truly decompose it. And that also ties into how you can make use of computing that's not necessarily concentrated, right? Workload focus wise, I already mentioned, we do a lot of, our primary focus is more on the commercial side of HPC. So we do a lot of Wall Street, a lot of Hollywood, a lot of medical and seismic. They just happen to be 4 parts of the US. We work very closely with Mayo, so they happen to be 4 geos of US. We're now also doing significant amount of database in memory analytics work. So massive data computing, and we just started this year non-numeric computing, large graph problems. In fact, we just submitted this week a large graph problem paper. And primary learning, if I had to summarize it in one word or one sentence, at least it may be a biased view, but I think a huge inefficiency lies in how algorithmically, there's a huge disconnect in how machine resources are used. So there's a big impedance mismatch in people's traditional thinking, and less in the case of HPC guys, but more in the commercial world out there. Traditional thinking on how algorithmically people have been approaching problems, it's very anti-parallel, the mass solutions that are out there. And thanks or no thanks to the kind of machines we've been building, largely single core machines, out of order, whatever. So that impedance mismatch is responsible for most of the efficiency loss, and the return you get there. It's like my advisor used to say, Mike Flynn, that time lost is lost forever. That algorithmic disconnect is a huge source of inefficiency. And just to give you one data point, we have achieved on this paper, on a single socket Nehalem graph problem, which is listed in top 500 with 256 nodes. So the 256x disconnect is because you need to sit down and really understand that algorithm in system-friendly terms. And the algorithms that are out there are really unfriendly in terms of the multi-core or the architectural trends that have happened. SIMD, caches, go on and on, the 3 or 4. So most of our papers are we're trying to understand how to bridge that gap. What's the new abstraction that can really bridge the gap and deliver efficiency? We got Best Paper Award at SIGMOD last year, same thing, right? It's for large tree search, graph search problem, huge inefficiency, not 10x, 2x. More than that lies in not being able to match the system trends with the algorithmic nature. So I was part of a National Academic Task Force which just concluded on sustaining growth in compute performance. And these observations somewhat come from there. And in interest of time, I'll just focus on the new or recent catalysts for compute. I mean, traditional catalysts for compute, I'm sure at least people here are very well familiar with. But I'll just emphasize what's recently happened is very important, and it's important to understand what's recently, what's new, what's now driving compute. And the first one is more, at least to Intel, to us, very important, which is changing demographics of computer users. Most computer users used to be people like me and you, with designing yet another machine, and for geeks and nerds. But the primary growth in industry is coming from a very different demographics of people. They could be farmers, they could be in emerging countries, and that's the people who, and those guys, the way they use compute and what they're looking for, the requirements are very, very different. People roaming around with phones or waving their hands. So you need to understand what it means to address their compute need. And compute requirements for them is not necessarily simple or cheap. It's multi-exaflop also. It's just a matter of understanding what the grandma wants, right? And video karaoke is not a simple application, it's a very expensive application, right? And who doesn't want? Of course, kids are jumping up and down with audio karaoke. Video karaoke would be even better hit. They wouldn't be jumping on a mat at Fry's. Now, but doing that is extremely difficult. So it's not a matter of end user not needing it, but how do you meet an end user need which has a very different user interface? He'll not sit and code Java or SQL is an important consideration. Then the second one is this is a point we are in. We are at a point where massive data is finally meeting massive compute. And massive data that's not just accessible to a government agency or some secret service, but accessible to all of us. That YouTube impact, that kind of Picasa impact on how you approach traditional problems is very, very important. So often we are able to now find massive data approaches to the traditional problems, and these are a lot more power friendly and a lot more, lot better approaches and algorithmically efficiency wise, and they've been known for some time, but the data just wasn't there. So you resorted to heuristics which rarely worked. So the last one being connected computing, the fact that it used to be very difficult to find a machine which was connected, and now it's the other way around. So how do you take advantage of these three trends? And in my view, these last three trends on who the real computer users are, the guys holding iPhones or not even holding iPhones but sensors embedded, and villagers, and the convergence of massive data with massive compute, I think first time in the history of computing, finally, fact that it's all connected has huge implications on how we've traditionally viewed problems and how we can derive efficiency. So we have been spending a lot of time in understanding and modeling such problems, right? What is at the crux of it? How do we really model such applications which can be like all those Hollywood to Wall Street type applications? And this is, you can probably find reference to this in our IEEE proceedings paper. We explain how our workload view, but this is our view of understanding or modeling these. And all these applications at very high level, you're basically asking the simple three questions only, right? What is it? And that's really at the crux of computer trying to understand what is that you're after. You could be the object or event that the computer is trying to model, that the user has in mind. It could be a flower, it could be a terrorist, it could be stock trading opportunity. Some event or object is the what part of it, right? And huge amount of cycles go in just modeling that object. And if you have a good model of that object, you'll have a good output. But the goodness of the model at the end user level is only judged one of two ways. The output of the mining, like can you find me similar things? Can you find me flowers like this? And go Google it. Go back in the past and find something similar. If you're good at finding what I'm looking for, you must know what I mean. Or synthesize, simulate in the future. If there is no such a flower or Madonna that exists, create such a one, create some such. So synthesis or mining are the only two ways an end user, a grandma or grandpa, really judges the goodness of the model that computer has. Now, what the power of massive data is that these models can now be refined real time, continuously, as opposed to just hoping and praying for a good model. And that's why you have to be able to iterate. And for most problems, we're not as lucky as the typical Navier-Stokes type, where you have a deep understanding of the problem. We have almost no understanding of the problem, especially behavioral problems. So in all these cases, massive data comes to rescue. We may not know the causality. We never be able to write that equation, but we can still track those problems. The problems become tractable because of huge amount of data. That massive data approach, and there are several examples of this, including the medical world for a huge amount of functional MRI data to figure out what the guy is thinking. Such bizarre examples to much more close to our usages where we can replace large matrices by just computing. So the centerpiece here is really the one that runs on the server side, because that's where the massive data will reside. Your laptop will never have enough data. But huge amount of data, hundreds of millions of images, will only be residing on the server side. So that inner loop is where that large amount of data is constantly created, and ontology is created and structured-fied, XMLized. And the outer loop is where the end user sits. So the end user, like it could be me or you or whoever is blogging or trading, that end user loop is generally a visual computing loop. Some image or some model back to the computer, and then model back to the image. Right? That's how you interact with the 3D world. So that outer loop is a visual computing loop, graphics and vision, and the inner loop is where the most of the compute and the server-side compute happens. Now, the power of all this is that we are now able to do the amount of compute that you need when you're able to reiterate real time. The best example of this is Wall Street, where trades happen in millisecond, not because someone is hitting a keystroke. That's too slow, right? Professor Norman analyzes a gap between how long you think. Because the trade happen, all program trade, you can actually go in milliseconds, and then once in a while, after some seconds, you are told whether your bot found something or succeeded or not. So the end user, human user, is still in the loop, but the machines now, the inner loop can go a whole lot faster than the human response time. So it's not even limited by how fast I can hit a keystroke, how many colors I can see. The inner loop can actually go a whole lot faster than the outer loop. So this is why this drives the insatiable need for compute when you have huge amount of data, because and it's being enabled because of the software infrastructure that's happening, XML and then some ontology language. So that URL to XML to some a basic RDF is what's driving this semantic web-like thinking, right? And that's really so the simple, our view of computing therefore is that the very outer loop you have humans or someone, and that loop is largely driven by sensing of some kind. It's currently driven by output. So your computers used to have you type a few keystrokes and you see a few keystrokes. Old machines. Something happened and now you type only a few keystrokes, but you get to see 3D view or 3D world. So it's been too much output dominated. It's only a matter of time with the cameras becoming so cheap, sensing the input side will dominate again. Anyway, the input side, the sensor, camera, or output visuals, where you have to go through a transform from whatever that FFT-like domain back to the flower building or color or user domain is very expensive task, but that's what will dominate the outer loop. Okay, and the inner loop will be massive data analytics. That's where the huge amount of data would only reside in some cloud, and that's the only time you can actually model the world with that amount of data, not with one user's data. So if that being our worldview of emerging applications and the compute model, it becomes the key driver where I want to spend just a few more minutes on is really this opportunity of massive data computing. This massive data computing has big implications on how we build computer, how we efficiently use them, and it's not simply a matter of going from LinPack to Graph 500, which you're already seeing in HPC world. It's a whole lot more than that in terms of its implications, right? And like I said, the whole data-driven models are basically letting us track or address problems which so far were unaddressable because no scientist gave us that nice equation formulation, some PDE to solve. A whole bunch of problems now become tractable, even though we may never have that closed form or analytical understanding just because we have large amount of data. And the connectivity is a big boost here. That internet has almost in quality reliability you'll call a burn-in effect. It speeds up things big time. As opposed to me trying to train the system on what I talk, how I look, that instead of tossing a coin million times, the coin gets tossed, million coins get tossed in a second. So the learning happens amazingly fast on the web. And Google may have no notion of who some Indian politician is, but if that guy is popular, 5 seconds later, Google knows all about it. Not because I'm constantly asking a question, whole number of, all kinds of people are asking right away. So that learning, that connectivity, and that real-time training where you can start with a very poor model, but you quickly improve it, is at the heart of this massive data computing. So now I'll spend a while where I think the most relevant from the point of view of audience here is our, at least application-centric view of where the energy efficiency opportunity lies. Clearly it's a biased view, but we believe that there's a huge opportunity in really re-understanding or recasting or understanding these problems from the emerging applications and realizing how to map them most efficiently on the multi-core, many-core trend. Because if you don't think, the two are very, very different. Take, for example, a large graph problem. If you simply take a problem and map it, almost every node, every vertex will be a page walk and be huge and efficient. And you conclude that I need megawatts for building or for doing these connectivity social network problems. Reality is there's a huge inefficiency in how that problem gets computed today. Because of the algorithms, the machines, the locality, the core friendliness, thread friendliness, cache friendliness, SIMD friendliness, none of that stuff exists. And the parallelism is really infinite of what kind? Of data kind. It's a huge amount of data that's at the heart of parallelism here. So you have to be very, very efficient in dealing with data parallelism and unstructured, irregular data parallelism. Because a huge amount of parallelism lies along a dimension where you may not have seen. So that's where the whole opportunity lies. So the first part is also realizing that most of these emerging applications are not like calculating the balance in a bank statement. These are all statistical problems. There is no good output. There's no perfect search output. It's just more compute. So there's a nature to it, statistical nature to these problems, and that's what makes it very attractive, very appealing to match that statistical nature of the problem with the nature of the system we build, which will be increasingly failing all the time for all kinds of sub-nano reasons as well as data center reasons. But you deal with them at a software level and algorithmic level. That's a more efficient place to deal with them as opposed to at the very lowest level. And locality awareness, data and compute, the examples of these few papers we have recently published, everywhere it's a 10x, 100x type efficiency gap lies in not being able to understand the core and compute density and what's growing and what's not growing. Bandwidth is not growing. So you have to be really understanding of the locality aware programming and locality of a working set of your problems. Working set used to be only a matter of cache megabytes, and people never worried about working set after that. You need to understand the working set at a higher level of the kind of near memory systems and flashes and embedded RAMs that we can now build. And then you see a big opportunity, not just for typical JPEG MPEG compression, but compressing, like this graph problem we're talking about. We took an entire billion vertex graph, and each vertex is just a bit. So the entire cache of few megabytes, tens of megabytes, only holding a bit, one vector, one adjacency vector. So those kind of compact data structures is how you get a huge cache locality. Otherwise, the entire thing will be missing all the time. So it's parallel and distributed decomposition, and doing it efficiently is where I think real efficiency opportunity lies of 100x or more. So now my time is up. So I'll just do the part which I'm not very good at doing anyway, which is our product pitch. So we do have, so all designed this way. And so the very first thing we're doing is we're building a product line primarily for such applications where key trade-offs have been made to increase compute density, to improve bandwidth efficiency by offering scatter gather, by building and trading off single core performance with a more parallel core. And there's no free lunch. You have to make a fundamental trade-off which has not been made for a long time. We're slowing down the AMDAL, scalar part of AMDAL, by offering even higher parallelism. That AMDAL doesn't normally couple them. When you couple them, you get an optimization problem. So you would not necessarily see a speed up unless you have enough parallelism. And this is this line of many integrated core, which I was with our senior VP, Kirk Skaugen at Supercomputing this past summer, and where I co-launched this with him. And this is our new product roadmap, which basically offers, like I said, a higher compute density platform for such emerging applications with large amount of parallelism and with this challenge where you really have to trade off your compute for single thread compute for more parallel compute, right? And then you get terabytes per second, but the terabyte per second is on the on-die ring, and that's where it'll be easier to get byte per flop, not on external memory subsystem. So this software development platform is available now. It was available this summer, and the first product will be available second half of coming year, 2012. And as you can see, our goal here is, at least the numbers we are seeing, you see the trend that you've been seeing for multi-core gets significantly boosted for this class of problem only. It's not going to happen unless if you don't have enough parallelism. But you see a very significant boost in performance for all those traditional impact type applications. Now, whether this is enough to meet the exascale target, time will tell. But I'm personally very optimistic that this will. So this whole Knight's roadmap from Knight's Ferry to Knight's Corner and well beyond into exascale time frame is our new family of products. An important thing here is that it's the same architecture, the same 4 attributes: cache, core, thread, SIMD, same x86. So your entire tool chain just ports. No need to learn radical architecture, radical language. It's an attempt to see how far we can go through our traditional approach, where for whatever reason enough has been invested, and people want the code to run fast, but they also want to code fast. So that's really the thinking behind this, and to be able to support this kind of heterogeneity, which is not an architectural heterogeneity, but a performance heterogeneity through a same tool chain and all of our tool chain. So this is basically my summary. As you can see, this is an unfair presentation. Second half got 2 minutes, and first half got 25 minutes. And it also kept the content simple, and the real reason was that Intel legal and marketing left me alone with content which it's not saying anything. And it's, yes, energy efficiency, I think applications understanding will play the most crucial role in getting the efficiency up. The huge opportunity lies in how a big impedance mismatch is there today in the core of computing that happens and the core of computing that's getting built. The algorithmic core is in a disconnect from the computing core that's getting built. Parallel stuff from anywhere, CPU, GPU. That disconnect is a big source of an efficiency opportunity. Plus, looking at the problems differently in the massive data world we live in, I think, especially if we can understand how to decompose them right to make use of the iPhones that people are holding, is a huge opportunity for filtering data right there before you take it all the way to data center. And that's where the efficiency opportunity lies, much more than getting efficiency out of right at the data center. A lot of bad things have happened when junk photos got uploaded right there. So that distributing and decomposing the problem and doing something right there in the camera itself is a better way of solving problem in my view. And I think there's increasing trend in how more and more such things are happening in a more distributed decomposition problem. And computing density and locality awareness are still the key.
Thank you. So we'll take a couple questions again.
Is your Aubrey Isle the same as Sandy Bridge?
No, this is just to give you numbers. So Sandy Bridge, a typical Sandy Bridge project, Sandy Bridge is multi-core. This is many-core. What's the difference in multi-core and many-core? Multi-core gives you the best single-thread performance, then few more cores because of that Ottolini observation that we can't keep increasing a single-thread performance without violating, without going out of power envelope. So you get highest single-thread performance and 4 cores or 6 core or 8 core. This is 32 core. So this is, roughly speaking, some few hundred gigaflops. Now you get a teraflop, 1.2 teraflop. So this is many core, right? So it's a P54 core with the same core. Before 10 years at IBM, I used to be at Intel. I did 3646 Pentium microarchitecture, microcoding. It's that core which I designed or helped design, the microcode part of it, 20 years back. So it's a very different computing platform. But same otherwise, right? You can still boot Linux, Windows, whatever, right? It's still x86, yeah. The big difference is in the memory subsystem and the internal, there's a big vector unit added. So big significant support for a scatter gather, that thing that we were just talking about, unstructured accesses, big vector extension. Sandy Bridge is 256, this is 512. So that extension, this is simply, in my simple view as a researcher, this is a leading indicator of problem or opportunity, many core.
Let me ask a question. So your group has spent a lot of time basically being clever, parallelizing applications, optimizing them. Have you encountered important applications that sort of defy that kind of optimization?
Yeah, yes, I mean, this graph problem was one such, right? We stayed focused on traditional floating point problems, and now the database problems were one big challenge, and the graph problems were even a bigger challenge. On the other hand, so far at least, we haven't found, of course, there exist problems which are very hard to parallelize, but almost everything we look at, thanks to large amount of data, the parallelism is, I say it always, that problems have been serialized. That's the real problem of last, that's the real thing we are paying for over the last few decades. Those problems are by nature very, very parallel. Almost every problem that needs compute is a parallel problem.
All right, well, thank you very much.
Thank you.
All right, so our final speaker for this session is Bikash Koley. He's the lead for the network architecture and capacity planning teams at Google. And I think for those of us who follow data centers, Google is certainly an example of a very large-scale operation with many interesting innovations and technologies. Before going to Google, Bikash was the CTO of QStreams Networks, which he co-founded. And so I look forward to his comments here.
Thank you very much for the opportunity. It's a great audience, and I think I just killed the clicker here. I'll see if it still works. I think the last two talks almost perfectly set up this talk to explain why very large data sets right now reside in cloud, And because they reside in cloud, the challenge that we face in scaling the cloud infrastructure, that in fact supports that data set, right? So that's what this talk is going to focus on. Great, it still works. So many of you have seen what Google's mission is, and this is the mission on which the company was founded on, and it is still our mission, which is to organize the world's information and make it universally accessible and useful. From the infrastructure point of view, this mission statement makes it an extremely challenging job to scale our infrastructure to meet this at the rate at which the internet is growing. And here is an example why that is. Everything that we do is about scale. And if you look at the scales that you're talking about, the world population is somewhere around 7 billion people. This is a bit dated data. The internet users are getting closer to about 2 billion. We serve more than a billion queries every day. Geographic distribution, it's a worldwide service, right? So our services are over 55 countries and 112 languages. More than 50% of our search queries actually come from outside of the United States, right? Data growth. The data growth has been explosive in the internet. On an average, billions of new modified pages are added in the internet. So in order to go and index it on an hourly basis or several hour time scale, we go and crawl the whole internet and gather more than the whole of Library of Congress in terms of the data that we go and collect. You have heard of a small site called YouTube where you go and watch video. Every minute, users upload 24 hours worth of video to that site. And much of that is actually in HD today, thanks to the easy access to HD video recording devices, including your phone, right? And of course, with that and being a global service, you have the obvious latency challenge, right? Bits don't move faster than light. And therefore, in order to provide users with information or answer to their queries in a time scale where the users don't perceive that they're waiting for the answer, which happens to be less than a second, you need to do something very specific in order to scale this infrastructure so that you are not killing latency in the process, right? So you have to address the latency issue as well. And one way that we found of answering a lot of these problems is by building our infrastructure specifically to scale to meet our users' need. And we do that by building something which we call warehouse scale computers. I'll go in a second as to why we call them warehouse scale computers and not data centers. There are some very, very distinct differences. The goal, though, is it goes back to what my previous speaker talked about, which is there are really two things that are happening when you're computing today. There is a visual part of your compute, and then there is a compute part of your compute. And that compute part of your compute doesn't need to happen on the device that you're using to access that. However, you should have similar experience whether you're on a phone, whether you're on a laptop, or whether you're on a tablet device, right? This is exceedingly important because people are accessing compute resources with devices that are not necessarily the highest performance devices to do compute, right? Your iPhone, for example, again, something that my previous speaker touched upon. In order to be able to do that, you need to build a backend infrastructure which takes the time-consuming part of compute away from the device that you're using to access it. And in order to do that, the way you do it is, again, what we call warehouse scale computing, right? And here is an example of a warehouse scale computer that we have built. This is one of our data centers in Oregon, and I'll point out a few interesting things here. One, as you look at it, you basically see two warehouses. They're full of computers. That's the simple reason we call them warehouse scale computers. They're literally warehouse full of computers. You notice that they're very close to a source of renewable energy. It's in fact really, really close to a hydroelectric plant in Oregon, right? So we're looking for most efficient and renewable and as much possible renewable energy to power these plants because they do take a lot of energy. You also notice these two towers, they're cooling towers. And I'll go into that in a second. They're not your traditional chillers. Chillers are actually extremely inefficient in cooling computing devices. So we have done tons of innovations in getting the energy and the cost, obviously, out of this cooling infrastructure, and I'll touch a little bit on that. So what's the difference between a traditional data center and a warehouse scale computer? Why don't we just call them data centers? So there are some couple of very interesting differences between them, which in fact leads to the main topic of today, which is energy efficiency. So in a traditional data center, the way it's built is your infrastructure is decoupled from the compute that goes into it. You basically build a shell and core. You come up with a way of cooling, and then you plan to cool certain heat load or certain energy load that you'll have in the data center. And you fill that up with compute equipments that are heterogeneous in nature. They could be various generations. They could be for various different usage. You have storage arrays. You have compute arrays. There could be various different networking equipment to connect them. And since you are designing your infrastructure, not quite knowing what compute equipment is going to go into the infrastructure, you're always designing for the worst case thermal load, which ends up leading you to build an infrastructure which is not quite energy efficient. How is that different from the way we do it? In Google's infrastructure, and Google is not the only one, there are other companies similar to us who are building this infrastructure in a very similar manner these days, where the design of the facility and the compute is integrated from day one. What that really means is that we build our infrastructure with utilities that are designed specifically for the compute equipment that goes in there. The same thing is true with cooling. The cooling is built to specifically cool the hardware that is going to go into that infrastructure. The flip side of that is the hardware is designed to be completely optimized to go sit in that infrastructure so that you get the best efficiency out of both. And that has huge value in terms of both energy efficiency and the scaling that you need to hit. So simplistically, how does this work? How it really works is if you go and walk into this data center, you're going to go and see rows and rows of exactly identical looking compute racks where the individual elements are really off-the-shelf computer with some modification that we do, and I'll go into that as well, where we do the modification. But these are really commodity hardwares. The commodity hardware, they're stacked up on racks with a set of switching equipment that basically helps you connect these devices or these servers, individual servers that go in there. They're then arranged in rows and columns of racks which are combined into a cluster, and they're connected by this cluster networking gear, right? So simplistically, that's all it is. However, there are a very large number of them. And as a result, they consume a large amount of power. And I think you heard before that if Internet was a country, it would be the 5th largest consumer of power today. It's right behind Japan, and it's right above Russia, right? The point is that it's not just Google. Most of the large Internet service companies build their data center in a similar manner because of the nature of data that you're actually processing. It's a very large data set, and you can process that large data set only with a certain type of infrastructure, and this infrastructure is here to stay. It's not going to go away. What it really means is that you need to do everything that you can in order to get the most efficiency out of this class of compute infrastructure that we're building, right, or various people are building. So one way of measuring efficiency in data center, and this is a method that EPA has used, and they have some roadmaps on that. It's called PUE. It's the power usage efficiency. And the way it's defined is the ratio of the total facility power divided by the power that is being used by the IT equipment. So a simple way of looking at that is if you look at your desktop computer at home, the PUE is actually more than 2. Which basically means that if you plug a desktop computer into an outlet in your home, more than 100% of the power, or rather whatever power you use in the computer itself, you waste almost the same amount of power in various places, including utility lines, the way the power is converted inside this equipment, the way the equipments are cooled. Some of that comes from the air conditioner that you run at home to cool this gear so that it doesn't overheat, right? The industry average of a generic data center, and this is a generic data center, this is not warehouse scale computers. The industry average of a generic data center is slightly better than that, but not terribly better than that. It's about 1.9. There is an EPA target of 1.2 in 2012 for the state-of-the-art data centers where everything has been done in order to get the most efficiency out of the energy that goes into the data center. This is something that Google has been spending a lot of time, energy, resource, and research on since the inception. I mean, that's part of the reason that Google's infrastructure went into what we call warehouse scale computing, and it is not done by traditional data centers. These are graphs of some of those, and I think goes back to 2007, I believe. There are a whole bunch of data centers that are plotted here. What you'll notice is that all of them are less than 1.3 PUE. We have come pretty close to less than 1.2 for all the data centers, and you're seeing many generations of computers and machines and other infrastructure that are in there, right? The key thing here is that we can say that compute is getting more power hungry because we need more and more number of those. There are certain things that are constant, which is how you design, how efficiently you get power into your compute mechanism, and there are a lot that you can do in order to make it efficient. This is a graph of one of our newest data center, where what you see is that we have actually hit less than 1.2. So really the way to read this is you waste, if you were to use 100 watts of actual compute power that goes into your computers where it runs the computer itself, you waste about 16 watts of power in that, which is, as compared to the industry average, it's 90 watts. So you've actually taken out a significant amount of power. There is another very interesting aspect of that, right? So you have often seen this alarmist view of, internet consumes this much power. Well, the truth is that compute in general consumes a lot of power. The more people are using high power compute, the more power they consume. If they're doing all that computing at their home computer, they're actually consuming a lot more power than if a lot of that processing is in fact happening in cloud, for two reasons. One, like I said, the home computers are actually not terribly efficient devices. They're in fact very inefficient. The second problem that you have is that because there is no statistical multiplexing of processes that are running on those machines, you're wasting significant amount of energy in spinning hard drive or running screensaver on your machine, where you are still draining it from the grid. While in these cases, since these servers are multiplexing a large number of compute process in the data center, the amount, the 100 watt that is actually going into these machines are real 100 watts that getting converted into compute. So if you do a global analysis of how much power efficiency you get by processing this large data into the cloud infrastructure, you actually have gain in two places. You have better efficiency in this cloud infrastructure, and you have better efficiency in how you use the infrastructure itself in terms of getting useful compute out of it. You remember in the first picture, I showed you a picture of this, which I call cooling tower, and I mentioned that it's not chilling. While designing these warehouse scale computers, we realized that chilling is a terribly inefficient way of cooling this equipment. That's where WSCs are different from traditional data center. In traditional data centers, you design them for generic equipment that you don't know from day one how they're going to look like. So you go and design them with the traditional way of cooling, which is more often than not chilling. These data centers have been designed for specific hardware, where there are specific designs with how air flows, how heat is taken out of these devices, right? What we did is we went and built, in fact, this is a significant invention that Google did. We built these cooling towers where what they are, it's very simple in concept. You basically run water around your servers. It uses as a heat exchanger. It takes the heat out of the servers. You get hot water that is pumped up to the top of this tower. It's run through a specially built tower where this is basically built with a special set of, a special type of material, which allows this water to evaporate very efficiently. As the water evaporates, it takes latent heat out of the remaining water. So the water cools down as it's going down. At the same time, you have this fans. This fan is basically sucking relatively dry air from the environment, and it's pulling it up. So it's taking the moisture out of the evaporation that has happened. And in the process, you basically have cooled the water, and then this water goes right back into the data center. So good. We have taken a lot of the cost of chilling out of the process, right? But fresh water itself is also very valuable, right? So it consumes energy to get fresh water. So what I do is we use recycled water. So what you're seeing here is this massive recycling plant that we have built within the data center, where I think one of the audience member had a question before where, the question was, how do you really marry your utility grid and other infrastructure to the data center? We actually are doing it today. It is done in a way that you are not wasting the energy of the utility in doing that outside and bringing it back to the data center. I'll give one other example that I have done, which is very interesting in this context. The latest data center that we announced that we built in Finland, it's built in a place which is around Gulf of Bothnia, where your average water temperature around the year is less than 40 degrees Fahrenheit. We don't do any cooling there at all. We use the water directly from that Gulf, the Gulf of Bothnia. We run that through the same system. We don't even need to evaporate because the water itself is cold. And we run it around the server to cool it down. So you have completely eliminated the cost of chilling. And that's how you're getting to a PUE very close to 1, where every bit of power that's going into your data center is actually getting used for useful compute. In addition to that, we actually have spent significant amount of time in building servers that themselves are energy efficient. How do we do it? We do it in multiple ways. We have taken out elements that are seemingly common in data center but can be very energy inefficient. UPS is a great example. When you have a common set of backup battery which gets charged and it may or may not get used and it's discharging, you're actually wasting a lot of energy in the process. What we have done is we have completely eliminated UPS. We have replaced them with small batteries that go on the servers themselves. So as a result, you have the small units that get charged, that gets charged or discharged if necessary, and you don't have the cost of distributing this backup power across the server floor where you waste energy. We have also eliminated, you may remember that I said that these things are built with commodity hardware. They look like standard motherboards, Intel or AMD-based standard motherboard that you find on the market. What it did do is we eliminated all the components that are not necessary for what we do. Graphics chip is a great example. We process graphics. We don't produce graphical rendering of the output, right? That happens in user's device, and therefore we don't need any graphics chips on the servers. We have completely removed that. We have optimized the fan speed. Fan is a killer waste of energy on your servers, and you can do significant optimization in how these fans run. We have optimized fan power. The goal really is energy proportionality. I'm almost out of time. I'll basically leave you with this one last slide, which is kind of similar to what many of my, actually both of my previous speakers pointed at. The new Moore's law, as we talked about before, is addition of cores. It's not scaling of the clock speed, which works great for what we do. This is again something that my previous speaker pointed upon, right? This is the data set that we are actually dealing with. So parallelism works extremely well with what we do. The problem though is that Moore's law has allowed us to get to higher number of cores without increasing without costing us too much more. We do need more and more compute in order to scale the way our services are, which essentially means that the proportional cost of energy as opposed to compute is growing by every day. So what you really need is energy proportional computing, where in fact it's not only just the cost of compute, but the power consumption that it takes in compute to go down as we grow in terms of efficiency and the ability to compute more. So there are a few other things that are interesting with this large-scale data center. Networking is a very interesting piece of it as well, where it's important to get the cost out. I would not have time to talk about that today, but I mean there are other places where we talked about that. Energy efficiency is something that as a company we take very seriously. We have spent significant amount of research where we are very interested in working with researchers to get the most energy efficiency that we can get on both our compute platform and our networking gear. So if you have bright ideas, please email me, please come contact Google or anybody that you know there. I'm happy to be a contact point if you have bright ideas there. And thank you very much for listening.
I have just two questions. One is, you said that the coolers are made of a special material. What material is that?
I don't think I can get into a lot of details of that. It is standard material which is designed to maximize the evaporation of water.
I see.
It's
Okay, and then your permeable building, which you house the coolers in, why do you use a building? Power plants are made without buildings encasing them.
sorry, I didn't quite get the first part.
Permeable buildings you showed on your chart that house the coolers,
Yes.
why do you encase the coolers in the building? Power plants are traditionally just out in the open,
Are you just talking about the cooling tower or the building itself?
the building.
So the building houses the computers, right? So there are other things that are in that building. The cooling towers happen to be at the top of the building, which is still outdoors.
Oh, it's not the whole building?
No.
Okay.
No.
Thank you.
So yeah, so if you look at the first picture, you can kind of see it there. So that's the building and that's the cooling tower at the top. It's the same with both. Sure.
So how much power does this complex need?
I'm sorry?
How much power do you have to have for this complex?
It's in megawatts. That's all I can say.
Are you extracting the water from the river for your cooling needs?
So we recycle as much as we can. So yes, we are always close to a water source, so we can get water that. So keep in mind this water doesn't go back to the river or the Gulf or whatever. But yes, we are typically close to a water source where we can get easy access to water, preferably in cold temperature, if we can.
Okay, since I'm interested, let me give you a minute to say something about the networking component of this.
Sure. Excuse me. So I'll go through it very quickly about the networking component. So cloud infrastructure, it's actually extremely important to connect the compute gears with each other so that you can sort of virtualize where your compute infrastructure is in place. So you don't want your service to worry about where your storage is or where your processors are or where your RAM is. Literally, you want them to give a layer that they run on and it's virtualized in software. In order to do that, it's extremely important to have connectivity between the servers so that the network itself is not the bottleneck, right? So what you see really in a data center fabric is that the further you are from the, so if you take two compute elements, the further they are physically, the less bandwidth that they have. And this typically has to do with how they're actually connected in the data center, right? So you find out that when you have this large number of machines, you can never buy a networking equipment that is large enough as a single element to give you the connectivity that you need for them. So you always have to build a fabric in order to build the cross-sectional bandwidth that you need for these servers in order to give you the bandwidth that you get. There are many ways of building this fabric. There are a whole bunch of published work on how they're done. There is fat tree, torus, flattened butterfly, a whole bunch of ways of doing that. One common thing there is, if you really look at their architecture, in this specific case, I just picked fat tree for really no reason. This is very commonly done in literature. What you end up finding is that in order to get constant cross-sectional bandwidth, you actually need certain number of radix. So the way you build this fabric is by using parallelism out of the switch. Now that has some very interesting implications. So if you look at a switching element, now the switching element can be a chassis that you build from, that you buy from like a Cisco or a Juniper or Fortune or whatever, some equipment vendor that's out there. Or it could be a single switching ASIC. Either way, if you assume that your envelope of power and space is constant, the amount of switching that you get in the silicon is really determined by two things. It's determined by the CMOS generation that you're in and the pinouts that you get. And it's either pinout or I/O, either way, right? That sort of determines how many bits per second you can switch in that silicon, because you really have a gate count limit that determines your power envelope, right? So given a constant power and space envelope, you have certain amount of switching. Now, take, for example, you have a chip that gives you 1 terabit, or a chassis. I mean, I'm just using this as an example, that gives you 1 terabit of switching. You can take that 1 terabit of switching and you can present that to the fabric in various different ways in terms of your port speed. You can say, okay, 1 terabit of the chip will give me 100 IOs at 10 gigabit per second, or 25 IOs at 40 gigabit per second, or 10 IOs at 100 gigabit per second. Keep in mind that when you're increasing the speed, the number of IOs that you have out of the chip is actually going down. Now, that has some very interesting implication. So for various reasons, you actually want your IO speed to go up because that gives you better efficiency in the fabric. When you build a large fabric with large parallelism, unless you have perfect hashing, you are going to get inefficiency. And the larger it is, the larger your inefficiency is, and that has various implications on the usage and the energy and et cetera, right? However, if you run them at higher speed, that means your radix, the number of IO that you have on this switching node actually goes down. And as a result, what ends up happening is that in order to build the same cross-sectional bandwidth, you start needing more and more stages in your fabric as you go with higher speed. So that leads to a very interesting effect in terms of power consumption. Since we are just talking about power consumption, I'll just focus on that. It has other interesting effect as well. When you go and look at higher speed I/O, and higher speed I/O is actually great. We love that because it simplifies the design. You need less number of fiber. You get more efficiency out of the fabric. Typically, the new technology comes at a cost of both cost, dollar numbers, and power consumption as well. What you typically see is that when a new port speed comes, you typically get like, so let's say you have a 10x increase in port speed. You're going from gigi to 10 gigi or 10 gigi to 100 gigi. It typically comes at a power premium. You end up consuming more power at that port speed. It's about 20x this day in the very early days. I mean, that happens to be true with 100 gig right now, if you compare that with 10 gig. Eventually, the technology matures and you get power parity, where on a per gigabit basis, you're consuming the same power to go in and out of your system. And then eventually, it basically gets into a mature phase where you actually consume less on a per gigabit basis with the higher port speed, which happens to be the case with 10 gigabit per second today if you compare that with a gigabit per second. So if you go and compare the power consumption on a gigi interface versus a 10 gig interface, 10 gig interface actually has less power consumption on a per gigabit basis. So it's consumed about 4 times, right? If you try and build your fabric, so again, if you go back into your design, and if you try and build your fabric for certain given cross-sectional bandwidth, and in this specific case, I think the example is for a terabit fabric, possibly. I actually don't remember what exactly it is. What you end up finding is that because you're reducing your radix count when you're increasing your port speed, you end up needing more number of chassis or nodes to build the fabric because you end up needing more stages. And as a result, the only way you can scale this with higher port speed is when your power consumption, in fact, goes down on a per gigabit basis when you're going to higher speed. This is a very interesting challenge for the researchers that are working on photonics, especially integrated photonics and silicon photonics. So when you're going to the next step of speed, whether it's through parallel wavelengths or whether it's through parallel bit stream or higher modulation scheme, keeping power parity is actually not good enough. You, in fact, need to shoot for 10x equivalent bandwidth for 4x power. And this math pretty much works universally for almost all the fabric architecture that people use. We actually have used this math for other fabric architecture. Until that happens, it's hard for data centers to go use it. Because, again, we have a finite power envelope in the data center, and we cannot scale that up by 4x or 2x. So we need to stay within within that scale. And that's actually a very interesting research problem as well that I would love you guys to address. Thank you.
Well, I want to thank all the speakers today. It's been a great day and a great session. And invite all of you across the street to the Coral Casino. It's on the beach, so if you haven't been there, it's a delightful location for reception. And we have a couple of wineries serving wine, which I hope you'll try out. But I want to advertise one of them in particular, our very own Jim Honey, who works on nitrides. His family owns a winery, Honey Vineyards, and Palmina is making the wines out of it, and they've actually won a bunch of medals for it, so I think it's actually quite good. So if you see the guy behind the table, he's actually just about graduated grad student in this area, but has a side hobby. So please enjoy, and we'll see you back here tomorrow morning.